We had y prime equals 7, y to negative 2, and we're given a point or initial condition that when x is 1, y is 3. We know that we cannot use this notation. We have to replace it by dy over dx equals 7 over y squared. Basically, I'm going to cross multiply, and I have y squared dy equals 7 dx. And now I'm going to integrate. And I will use only one constant of integration. So I have y to the third over 3 equals 7x plus a constant c. I'm given the point 1 comma 3. So when x is 1, y is 3. That will help me determine the constant. I can multiply both sides by 3 first. Y to the third equals 21x plus 3c. And at this point, I can plug in. So if this is 1, so I have 21 plus 3c. This is 27. So 27 minus 21 is 6. So then c equals 2. I go back and I put it here. So then I have y to the third equals 21x plus 6. And now I will have to take the cube root from both sides. So y equals the cube root of 21x plus 6. Any questions on this? Is this okay? Anything else? Anybody has anything else for me? Okay, the last short chapter of this course deals with functions that have more than one variable. And that is under the umbrella of functions of several variables. Functions of several variables. Well, we're dealing only with functions of one variable, something like this, let's say. But now we're going to look at functions that have, let's say, x and y and z. How will this look like? I don't know. X squared y squared plus 3xy plus 2z squared. Oh, sorry. So far we've been dealing with functions that have only one variable. This is one variable, this is another. The independent and the dependent. But now we have, for example, 3 independent variables and 1 dependent variable. So x, y, and z are all independent, and f is the dependent variable. So in section 6.1, we are only learning how to evaluate these functions and find domain. That's all we're going to deal with in 6.1. So here's an example. I just gave you an example with f of x, y, z. Let's say, can anyone give us a triple? A triple meaning a value for x, a value for y, and a value for z. So we can plug it in. Unfortunately, you cannot use a calculator on this. Okay, I'm going to say 2, 1, and negative 3. So f of 2, 1, and negative 3 will be 2 squared times 1 squared. 2 squared times 1 squared is 4. Plus 3 times 2 times 1 is 6. And 2 times 9 is 18. So the answer is 28. That's all there is to it. That's how we evaluate. Nothing new. It's just that we have to be careful and plug in the corresponding values. And in this case, I had x, I picked 2 for x, I picked 1 for y, and -3 for z. I performed the calculations, and I would say when x is 2, y is 1, and z is -3, the function value is 28. Now, concerning the domain, what do I have to do to write the domain? So here's an example. It's number 11. Let me show you. It's number 11. It's right here, number 11. So we have a function of x comma y, just two variables, is the square root of y minus 3x. And we're asked to find the domain of this function. Okay, so what do I have to state? We've been doing this for 3 months. What is the statement that I have to write and solve? For any square root, what do I have to write?
Is it that it's greater than 0?
Yes, or equal to, but what?
What's under the root?
Exactly, y minus 3x. And this is it. You can move 3x to the other side if you want. There is nothing else you can do to this. So how do I write the domain? Well, with a set builder notation. So this time, this function has two independent variables, x comma y, so a point, x comma y, such that x and y fulfill this condition. This is it. That's all there is to it. Let's look at another. I'm going to create one. So let's say I have f of x and y as 1 over x minus 1 plus 1 over y minus 2. Can anyone tell us what conditions I have to write, what restrictions for the variables?
X cannot equal 1, y cannot equal 2.
That's it. So the domain will be written as an ordered pair, any ordered pair that fulfills the given conditions. That's it. Any ordered pair is acceptable as long as x is never 1 and y is never 2. Give me any ordered pair other than 1 and 2, 1 for x, 2 for y, and I can give you a value. For example, you can say find f of 0, 0. Fine. So I have -1 minus 1/2, which is -3/2. But if you include 1 for x or 2 for y, I'll say sorry. I don't have an answer for you because the function is undefined. And that's it. Good. Of course, like with all the other functions, after we talked about the function, we found its derivative. And we also found its second derivative, and so on and so forth. Okay, the same thing follows now, but this time for a function of two variables. Okay, so when we determine the derivative for a function that had one variable, we use the notation other than f prime. We use the notation dy over dx. The same thing for the second derivative. We use the notation d2y over dx2. Notice that this is the regular d. Well, in our case, when we get to right now to differentiate functions of several variables, we can no longer use this notation. This notation signifies that y is a function of one variable. If I want to determine the derivative of this function, I have to pick one variable to differentiate by. I cannot differentiate with respect to x and y at the same time. Also, meaning this, I will differentiate the function with respect to x, but I have to think that y is a constant. I can differentiate the function with respect to y, but when I do that, x has to be kept or thought about it as being a constant. And the notation is different. Although it's a cumbersome notation and we have a shortcut or a different shorter notation. So when I differentiate f, because it's not a function of one variable, we're not going to use this symbol, we're going to use this symbol. So it's called the partial. Why partial? Because I cannot differentiate with respect to x and y at the same time. So this is a partial derivative. Which one? Is the derivative in which I differentiate with respect to x, but y is kept constant. I'm going to put in parentheses for this one. Y equals constant. I also have a second partial derivative. It's not the regular d. It's a roundabout d, if you want. Okay? So this is also a partial derivative. But it's the partial derivative of f with respect to y, meaning x is considered constant. So this is what we need to practice now. How to find the derivatives. The partial derivatives of a function with two variables. Because this notation is cumbersome, we're going to use a simpler notation. This is fx. This is not f parenthesis x, is not f of x. This is fx. Fx means the partial derivative of f with respect to x. And obviously this one will be fy. So I'm going to write them one more time so you can see them here. So we have fx, we have fy, we also have fxx. What is this? I differentiate the function with respect to x and I differentiate it again with respect to x. So this will be the second partial derivative of the function f with respect to x. And also we have fyy. And yes, of course, we also have fxy and fyx. And that's it. I promise, only this 6. Okay, let's see again what they mean. This is the first partial derivative of f with respect to x. This is the first partial derivative of f with respect to y. This is the second partial derivative, meaning I differentiate with respect to x and then I differentiate with respect to x again. The same thing here, the second partial derivative with respect to y. After I differentiate with respect to y, I differentiate again with respect to y. What are the last two? First, I differentiate with respect to x and then with respect to y. And first here, I differentiate with respect to y and then with respect to x. These last two must be the same. Okay, so let's look at an example and determine all 6 partial derivatives. And of course, you know what's going to follow. After we determine derivatives, what are we going to find? What do we do after we found the derivative for, or f prime of a function of a single variable? What did we do afterwards? What did we find for the function? What were we interested in?
The antiderivative?
No, we were not going to go that far with this, with partial derivatives or with multivariable calculus. No, we're going to find max min. Critical number, max and max min. Good. So now let's choose a problem and determine fx, fy, fxx, fyy, fxy, fyx. Okay. So I want to choose one in which we determine all of them. fxx, fxy, fyx, and fyy, and we will also determine fxy and fyx. All 6. Okay, let's look at 37. Just a function. I just want to copy any function. So fxy is x squared plus y cubed. And let's see how we determine all these 6 derivatives. Fx is very simple because I differentiate with respect to x. I consider y a constant. So this is 2x. Nothing else. Now if I want to determine the second fxx, I differentiate this function with respect to x and I get 2. And this is done. Okay, now let's find fy. When I differentiate with respect to y, everything else is constant. So then I have 3y squared. Can anyone give us fyy?
Six.
6y. Very good. And what about fxy? It means that I differentiate with respect to x the first time, and now I differentiate with respect to y. If I differentiate with respect to y, everything else is a constant. So this will be we differentiate this with respect to y. So what do I get? There is no y. And now let's differentiate fyx. Let's differentiate this with respect to x. Remember, these have to be the same. When I differentiate 3y squared with respect to x, what do I get?
Is it still 0?
That's it. This was a very, very simple example. Very good. I want to choose another function. Let's say f of x comma y equals x squared plus xy plus 3y squared plus 11x. So we want to determine fxx, let me put it here, fy, fyy, fxy, and fyx. All 6. Good. So let's start. When we differentiate with respect to x, we only look at x and nothing else. Nothing else counts. Everything else is a constant, even if it doesn't look like it. So can anyone give us fx?